Hello, this is Professor Roman. Let's continue with the lecture series, Transition to Advanced Mathematics. We have finished our discussion of the propositional calculus, and so now we're going to turn to the predicate calculus. As I mentioned before, the propositional calculus is simply not powerful enough to serve as a logical foundation for mathematics. There are a number of reasons why, one of which is that there is no way to express within the propositional calculus two very important concepts that we use a lot in mathematics. One is for all objects something happens, and the other is there exists an object for which something happens. These are quite common in mathematics. In fact, sometimes they're hidden. For instance, if you were to say the square of a real number is non-negative, what you are really saying is that for all real numbers, say x, we have x squared bigger than or equal to 0. So there's an implicit mention of for all in this case. So to incorporate the ideas of for all and there exists, we use what are called quantifiers. And in both cases, quantifiers require a set or class, which I call U, known as the universe of discourse, or simply the universe for the quantifiers. So here is the formal definition. Let U be a universe of discourse. So U is either a set or a class. A universal quantifier over U is an expression that looks like this. And this is read for all x in U. If the universe is clearly specified beforehand, you can simply write for all x. The variable x is called the subject of the universal quantifier. An existential quantifier over universe U is an expression that looks like this, and it is read, there exists an x in U. And again, if the universe has been clearly specified, we can just write there exists x. And notice that everything is enclosed in parentheses for reasons that will become apparent as we continue. Also, in this case, x is called the subject of the existential quantifier. Now, the intended use of quantifiers, of course, is in that they be incorporated into symbolic expressions, into well-formed formulas. So here are a couple of examples. For all x in R, x is greater than 0 and x is less than 5. There exists an x in Q such that x squared equals 4. A well-formed formula that looks like this is read for all x in U, P of x, or P of x holds, or P of x is true, something like that. And in this case, there exists an x in U such that P of x holds. Since the subjects of a quantifier range over a specified universe, the choice of that universe has a profound effect on truth value. For example, the statement there exists an x in R such that x squared equals 2 is true. But if we reduce the universe, there exists an x in Q such that x squared equals 2, this is not true because no rational number has the property that its square is equal to 2, which is something, by the way, we'll prove when we get to proof techniques. So again, if the universe of discourse is clearly specified, it's common to omit explicit mention of the universe within the quantifiers. So, for example, if there is a statement that says the universe is the set of real numbers, then this well-formed formula, there exists an x in R such that x squared is greater than or equal to 0, and there exists a y in R such that y squared equals 0, could be shortened, and often is shortened, by dropping the mention of the universes. This is a little bit more readable, I suppose. But if the quantifiers range over different universes, as they do in this case, then of course we can't drop them. Despite all of this, you are going to encounter expressions involving quantifiers where the universe has not been explicitly mentioned. You shouldn't have to see these things, but you will. So if you see an expression such as for all x, x in R implies x greater than or equal to 0, the universe over which x ranges is not explicitly mentioned. Whenever that's the case, we will assume that the universe is the class of all sets. So basically it covers everything we might need. So this expression really means this: for all x in sets, x in R implies x greater than or equal to 0. Examples. To write the phrase, all apples have spots, in symbolic form, you recognize the presence of a quantifier, the universal quantifier. First, we need not variables, but expressions involving a variable. A of x is the statement x is an apple, and S of x is the statement x has spots. Then, if the universe is the set of all apples, we can write there for all x in apples, S of x, all apples have spots. If the universe is the set of all fruits, then we would have to write for all x in fruits, A of x implies S of x. If it's an apple, it has spots. This would be incorrect for all x in fruits, A of x and S of x. What this says is that all fruits are both apples and have spots, or in other words, are spotted apples. That, of course, is not true. There's plenty of fruits that aren't apples at all. Okay. So you may want to study this a little bit until it makes pretty obvious sense. Multiple quantifiers occur quite often, and so it's important to gain some experience with that. Here's an example. This is the definition of a rational number. R is a rational number if there exists a p in z, z of the integers, so there exists an integer p, and there exists an integer q such that, or for which, or some phrase like that, q is not 0 and r is equal to p over q. This is precisely what it means for r to be a rational number. It's the quotient of two integers where the denominator is not 0. To translate for every rational number r, there is an integer that is greater than r. We would write for all x in q, for all rational numbers q, there exists an integer z such that z is greater than x. When multiple quantifiers appear consecutively like this, the scope of each of these quantifiers is the same as the scope of the last one. So the scope of there exists an x, a z in z is z greater than x. The scope of the universal quantifier then is the same, z greater than x. So both of these occurrences of variables are in the scope of both of these quantifiers. For adjacent quantifiers of the same type, both universal or both existential, we can do some shorthand. For all x in u, for all x in u, for all y in u could be replaced by for all x and y in u. And there exists an x in u and there exists a y in u could be replaced by there exists an x and a y in u. When quantifiers are incorporated into the logical framework of the propositional calculus, the result is called a predicate calculus. We've already discussed the language of the propositional calculus and the construction of well-formed formulas for the propositional calculus. We could do the same for the predicate calculus, but it's rather more complex. It has to be powerful enough, after all, to be able to express a large variety of mathematical statements, which the propositional calculus cannot do. In particular, the language of the predicate calculus requires symbols that not only represent variables, but also constants, functions, relations, which, by the way, are called predicates. And all of these are critical to mathematics, so they have to be incorporated in the language. If you look back at the example with the apples and the spots, this is a predicate. It's a relation with just one variable. So there are predicates required to do the predicate calculus. So rather than go into the details of what the language looks like, there have to be symbols for variables, there have to be symbols for constants, there have to be symbols for functions of one variable, two variables, three variables, whatever, however many variables. Same thing for relations or predicates. Since this isn't a course in logic per se, we don't need to get into those details. Your intuitive feeling that you get from the examples and so on should be enough to, should be sufficient. Okay. There are two concepts, however, we need to be especially careful about. One is the scope of a quantifier. The scope of a quantifier is that portion of the well-formed formula that's contained within the first set of enclosures that immediately follow the quantifier. So here are two examples that should clarify. Here's a universal quantifier. Immediately following that quantifier is a bracket, and here's the ending bracket. So all of this falls, this expression here, falls within the first set of enclosures immediately following the quantifier. So all of this is within the scope of this quantifier. In this case, the scope of the existential quantifier is everything in the within the first set of enclosures. So that's just this portion here. That's just x greater than 0. X squared equals 1 is not within the first set of enclosures that immediately follow the quantifier. So the scope, so this is not included in the scope of the quantifier. Okay. Basically, you write down a quantifier, you immediately write down enclosures for the scope. The other concept that's very important to understand is that of free variable and bound variables. And we have to be a little careful. That terminology is a little misleading. When it comes to determining whether or not a variable is within the scope of a certain quantifier, each separate occurrence of the variable has to be considered separately. And I got to explain that. First of all, what do I mean by occurrence of a variable? Well, if you look at this simple expression, this x is an occurrence of the variable x. This x would not be counted as an occurrence. If it's the scope of a quantifier, if it's a subject of a quantifier, it's not counted as an occurrence. Okay. So I can go back here. Take a look at, say, this expression. There are two occurrences of x. So that's all that means. These are separate occurrences. Same variable, but separate occurrences. An occurrence of a variable is said to be a bound occurrence if two things happen. The variable lies within the scope of a quantifier, and it's the subject of the quantifier. All other occurrences are called free occurrences. So I think an example will help clarify. In this expression, there are two occurrences of x. The first occurrence is within the scope of the quantifier, and it's the subject of the quantifier, and therefore is bound. This occurrence of x is not within the scope of this quantifier. It is the subject of the quantifier, but it's not within the scope. So it's really kind of irrelevant. It really even shouldn't be referred to as the subject. So this is a free occurrence of x. Let's look at this example. Now we still have two occurrences of x, but they're both not only within the scope of the existential quantifier, but they are the subject of that quantifier, and so they are both bound occurrences. It's very dangerous to say a variable is free or a variable is bound. You must refer to an occurrence of the variable. If there's only one occurrence, one gets a little bit sloppy and might say x is free or x is bound. But as soon as there are two occurrences, that phrase is ambiguous. Okay, so you should, for practice, always include the word occurrence. Here's a well-formed formula. Now x, this occurrence of x, is within the scope of the universal quantifier. It's within the square brackets, and it's the subject of the quantifier, therefore it is bound. This occurrence of y is within the scope of this existential quantifier. It is the subject of the quantifier, therefore it is also bound. In order for a well-formed formula of the predicate calculus to have a truth value, and therefore to be considered a statement, every occurrence of every variable must be bound. There can be no free occurrences of variables, because then we don't have a truth value. For example, for all x, x squared greater than or equal to 5, or x greater than or equal to 1. Now, this x greater than or equal to 1 is not in the scope of this quantifier. It would have been perhaps a little easier to see what's going on if I had changed that x to a y. But I deliberately left this an x because you need to get used to the idea that just because one x is bound doesn't mean the other x, all other x's must be bound. Okay. This has no truth value. The first part has a truth value for all x squared greater than or equal to 5. That's false. But this is, there's some unspecified information here. Do we mean, what's the universe for this x? We don't know. Do we mean for all x in the universe, x is greater than or equal to 1? Do we mean there exists an x in the universe for which x is bigger than or equal to 1? There's missing information here. This is not, this does not have a truth value. You can't say this is true, you can't say it's false, because you don't know what's going on. Okay. The terminology that covers this is the following. A well-formed formula that contains only bound occurrences of its variables and therefore will have a truth value is called a closed well-formed formula. Whereas a well-formed formula that contains a free occurrence, any free occurrence of any variable, is an open well-formed formula. So this formula is open. And it is, I forgot the theorem number here. And it is a theorem that a well-formed formula of the predicate calculus is a statement, that is, it has a truth value if and only if it is closed. So let's take a look at this example. There exists an x such that x greater than 0 or x squared equals 1. Everything is in the scope of the existential quantifier, so all occurrences are bound. This is closed. This is also closed. The occurrence of x is bound. The occurrence of y is bound. This is an open sentence because this occurrence of x is not bound. This is an open sentence because even though this occurrence of y appears in the scope of the universal quantifier, it's not the subject of the quantifier. So this is not a bound variable. This is free. So this is an open sentence. To translate a sentence such as some integers are even and some are odd, we could write this. There exists an x in z such that x is even, and there exists an x in z such that x is odd. This didn't print very well, did it? Okay, x. There's no problem here with the fact that x is used twice. The two uses of x are independent of each other. To avoid any possible confusion, you could switch this x to a y, but you have to be careful that you also change the subject of the quantifier. If within this closed, let's just ignore that for a minute, this is closed, if within this closed expression you change one x, you have to change the other x. Okay, you have to change the subject. So you have to be consistent. If this read for all, there exists an x in z such that y is odd, that would be garbage. Okay, it wouldn't be closed anymore. Let's take a look at some rules for translating some common phrases into symbolic form when they involve quantifiers. So we'll assume that U is the universe. Okay? A phrase such as all P of X are Q of X is translated into symbolic form as for all X in the universe, P of X implies Q of X, or if P of X, then Q of X. That's the same meaning as all P of X are Q of X. There exists a P of X that is Q of X, translates this way into symbolic form. There exists an X in U such that P of X and Q of X. Okay. There is a P of X that is also Q of X. So P of X and Q of X both hold for that X. It's really important that you stare at these long enough for this to become pretty clear to you. Okay, because they're quite different the way the translation goes. And many students will make the mistake of thinking that all P of X or Q of X gets translated this way with a universal quantifier here, and that's not correct. Let's try some others. For every odd prime x less than 10, the number x squared plus 4 is prime. So that is translated as for all x in the natural numbers, x is odd and x is less than 10 and x is prime, implies x squared plus 4 is prime. So what you see here is for every odd prime x less than 10, that's got three specifications: odd, prime, and less than 10. So these are spelled out here with conjunctions, because they all have to hold. And notice that I've used probably more enclosures than most people would. The curly braces here and the curly braces here, but I wanted this to be as readable as possible. I hope that helped. It's certainly legitimate to use all the enclosures you want as long as they're used legally. So sometimes it improves readability, sometimes it doesn't. You'll have to judge that on an individual basis. Frankly, it's even easier to read these things when you can use large enclosures, which you won't see very often in books, I'm afraid. And it's too bad, because it does make things more readable. So this is the same as this, but I think the larger enclosures have made it a little bit more readable. Some functions defined at 0 are not continuous. Translation: there exists an f in script f, which I said, so I'm defining the universe here. Let f be the family of all functions on R. There exists a little f in script f such that f is defined at 0, and it is not the case that f is continuous at 0. Some real numbers have a multiplicative inverse. There exists an x such that x is in R, and there exists a y such that y is in R, and xy equals 1. Okay. I didn't put a universe here, so the universe would be all sets, but this constrains the elements from ranging over only the real numbers. So real number, there exists an x such that x is a real number, so there exists a real number, and so x is a real number, and there's a y, real number y, for which xy equals 1, so y is x inverse. it would be better to clean this up. There exists an x in R such that there exists a y in R for which xy equals 1. When you read symbolic statements, you're going to need to include some extra words to help make the statement understandable. There exists an x in R such that, or for which, there exists a y in R such that xy equals 1. And that can even be it can even be written this way. There exists an x in R for which there exists a y in R such that xy equals 1. The negation of quantified statements can be particularly confusing. So let's spend some time looking at that. Here is the negation of for all x p of x. That has the same meaning, or is logically equivalent to, there exists an x for which not p of x. So here we have not for all p of x. And that's equivalent to there exists an x for which not p of x. This one, not there exists an x such that p of x is equivalent to for all x not p of x. Okay. This is again something you should spend some time with until it makes sense to you. You might want to revisit negations we did earlier. All cars are blue and some cars are blue. We negated those, and that will help maybe clarify this. Okay. But let's try an example here. To negate for all x, x greater than 0 implies there exists a y such that xy equals 1. We can write this, first of all, we just stick the negation in front of the whole expression. So that's not that's not the way you want to leave it. You want to incorporate the negation inside, especially if you're asked to do this on a test. According to these rules here, when you pass the negation across the universal quantifier, it becomes existential. The negation comes inside. This is just a reproduction of this. Now, what to do with this? Not, let's just call this P implies Q for a minute. Not P implies Q. Well, the simplest way to see what to do is to replace P implies Q by not P or Q, and then use De Morgan's laws. And I deliberately skipped a step here. I could have written some intermediate steps here, but I didn't want to, because I want you to think about how to get from here to here. It's good practice. You have to trust me on this. If you need to practice, or this stuff will never sink in. Okay. And so once you get to here, then the next step is to deal with this negation in front of this existential quantifier. You put the negation inside, this becomes universal, and this gets negated. So we finally end up with this. So what I would suggest you do here is read this aloud and read this aloud and see if it seems like they are the negations of each other. Okay. Here's another example. The negation of some people do not like cats. So I put the negation sign already here, but this phrase is, there exists a person such that for all cats, person X does not like Y, no cats, does not like any cats. So that's, some people don't like cats. When you say I don't like cats, what you're saying is I don't like any cats. Or for all cats, I don't like them. So again, the negation goes past the existential quantifier, becomes universal, and we have to negate what's inside the scope of the quantifier. And now this negation passes the universal quantifier, it becomes existential, and we negate what's inside the scope. Okay, repeat this. Not X does not like Y. Two negations, involution, negation is involution, cancel, X likes Y. All I did here is there were square brackets here, and I dropped them to get this statement here. For all people, X, there exists a cat, Y, such that X likes Y. Every person likes some cat. One final matter of great importance is expressing uniqueness, something we could not do in the propositional calculus, but we can do in the predicate calculus. An exclamation point is the notation used to denote uniqueness. So this expression would be read, there exists a unique X in U. There exists a unique X in U such that P of X. This is shorthand, really. Exclamation point is not part of the language of the predicate calculus. It's a shorthand. So in a sense, it's meant to be immediately replaced by this. And we better look at this carefully. There exists an X such that P of X and for all Y and for all Z, P of Y and P of Z implies Y equals Z. Now if we split this right here, what comes first is strict existence. There exists an X such that P of X. That's part of there exists a unique X such that P of X. But we need to express the uniqueness part. This second part here, what does it say? It says that if you have two sets, and if they both satisfy P of Y and P of Z, then Y and Z better be the same. That is the uniqueness portion. So the existence followed by uniqueness. It's two parts, and it's a conjunction. So this shorthand is expressing all of this, which is why this shorthand was invented. It cuts way down on the length of these formulas. But you have to remember that to do this, you have to do two things. To verify this, you have to verify existence, and then you have to verify uniqueness. Okay. This is not the same as writing there exists an X such that P of X and for all Y, P of X implies Y equals X. This isn't even a closed sentence. Okay. So I would think about this a little bit more and see why it's not the same as that.